I don't know. You don't know. You didn't know that. What? A final exam?
Yeah, she didn't make that up.
Well, you did it then. Wait, so we didn't, we didn't do that.
By random faults.
Right.
Yeah, I think that's all. Like,
Bro,
I think there will be additional like plugs and output.
bro, we have a final exam, bro.
For what the hell?
I don't know. Other.
It's a bit bullshit. Rather than asking to do the help with this, it's kind of relative.
Okay. 3 lectures left. Let's keep going on cellular neuroscience. And I want to, I was looking at thinking about the last lecture, and I thought I'd make a few more slides just to sort of explain this in hopefully simpler terms that, if you know this, you're going to hopefully understand it. Okay. And I want you to understand this because understanding how equilibrium potentials are generated and how the resting membrane potential is created is absolutely essential to then understanding how the action potential is going to be generated. So, equilibrium potential. What is the equilibrium potential again? Equilibrium potential is the place where the membrane potential, okay, where that membrane potential is at a particular level so that the concentration gradient of a particular ion species is balanced by the electrical gradient. Okay, so how do we calculate that equilibrium potential? Each ion that is dissolved inside and outside of the cell is going to have its own equilibrium potential, right? Because each ion has a different concentration of what's outside the cell and what's inside the cell, right? We've got some slide over here, right? Like if we look at all these different ions, right? They've all got different concentrations outside and inside the cell, okay? So what's going to control that equilibrium potential is only 2 things. One, what is the concentration ratio of the outside to the inside, okay? And what is the charge? What is the valence of that ion? Is it positively charged or is it negatively charged? Is it +2 or is it +1? Okay, so how can we calculate an equilibrium potential? So we've got equilibrium potential for sodium, equilibrium potential for potassium. We could do a chloride one, we could do a calcium one, we could even do magnesium if you wanted to. Nobody really cares about magnesium that much, but you could do it, okay? So what are the steps we need to take to use the Nernst equation to calculate the equilibrium potential? First step, what is the charge of that ion, okay? So what are the monovalent cations? What are the ones that have a charge of +1? Potassium, which is K here, and sodium. It's +1. They both just have one positive charge. The opposite of that is a chloride ion. Chloride has a negative charge of 1, right? Sodium chloride is a salt. It sticks together. Your table salt fits together because one has a charge of +1, one has a charge of -1. They like to stick together, okay? And then finally, we've got calcium. Calcium is a divalent cation. It has a charge of +2. Okay, so if you're going to use that equation, that Nernst equation, you're going to first know what is the charge? It's the valence. We also write that as Z here, okay? So +1, -1, or +2. Then all you have to do is look up what is the inside and the outside concentration of that specific ion. It doesn't matter what the concentration of any other ion is, okay, for the equilibrium potential. All you care about is this one ion, okay? So if it's potassium, okay, or let's say it's sodium, okay? Sodium has a concentration on the outside of 150 millimolar. Sodium has a concentration on the inside of about 15 millimolar, okay? So we just have to divide the outside by the inside concentration, okay? And then take the log of that. So a log is just a number. What number do you have to raise 10 to in order to get that outcome? Okay, so let's just work that out, right? So, and this is where I wish I had a pen on here, but okay, so let's say outside concentration for sodium, okay, Na here, right? Outside concentration is 150 millimolar. Okay. Inside is 15. What's 150 divided by 15? It's 10, right? What power do we have to raise 10 to get, right? So 1. Okay, so this equation here, so ENA is going to equal 62 millivolts times the charge of a sodium ion, which is 1, times the log of outside to inside, which is 1. So that's why we get 62 millivolts plus 62 for ENA. Okay. And now, what about for potassium? Potassium, let me look up what that potassium equilibrium, but what our concentration was there for potassium. I think it's 140 outside. So K is 140 inside. Very important to remember which side is outside and inside. Okay, so outside is like 5 millimolar. Okay, inside's like 140. Anybody with a calculator on them? Take the log of 5 divided by 140. I know we got a guy over here who's got a phone. Let's go. Maybe he's just texting his friend. I don't know. He's doing it? Okay.
Negative 1.4.
Negative 1.44. Okay. Okay, equals, okay, so the ratio, so log of that is negative 1.4. Okay, what's that times 62? Times 1, right? So 62 times 1 is 62 times negative 1.44 gives us about negative 90 millivolts. Okay. Negative 90. So that's going to be K, EK. Okay, and we've already talked about those two. What if I gave you like a different ion, right? What about chloride, for example? Right? What's the concentration of chloride inside and outside? We need to know first, what is the valence? The valence of chloride is a little bit tricky, right? It's -1. So instead of putting 1 into that equation, you're going to put -1 into the equation, okay? And then we're going to have to know what is the concentration of the outside and the inside. Maybe let's look over here. Let's just estimate it. Looks like chloride is around, I don't know, what's that look like? 120 outside in the interstitial fluid and maybe 5 inside. Okay, so 120 outside divided by 5. What does that give us? $1.38. Okay, so 1.38. Oh, I've lost my. Oh, good. I still so Cl minus. Okay, so now we've got about 1.38 for our log of outside divided by inside. What's 1.38 times 62 times -1? -85. Okay, so maybe we're at -85 here for chloride. Okay. God, I need a pen. Chloride down here. Is that clear? Yeah.
How do you get it? 52 millimolar?
Okay, we're not going to get into that in this course, but it involves like ideal gas law, the temperature, like, and how much charge relates to how many moles are in a thing. I'll take 421 or take 408 and I'll tell you all about it. Okay. I'll see you in 3 years. Okay. Hopefully you'll figure it out before that. Okay, so let's see here. So that's how we're going to get equilibrium potential. We just need to know outside divided by inside. Okay, take log of that, multiply by valence, multiply by 62. Okay, so that's great. So each ionic species has its own equilibrium potential. Okay, that's the place where the ion's not going to move anymore. That specific ion's not going to move anymore if you have the membrane potential at that level. Okay, but what controls the membrane potential? Okay, the actual membrane potential of the cell, not the equilibrium potential of an ion, but the membrane potential of the cell is determined by the equilibrium potential of each ion. So what is the out, and that's of course determined by the ratio of the outside to the inside of that. And then the permeability of the membrane to that ion, or to each of those ions. Okay, so what's permeability of a membrane? That is, how easy is it for an ion to go across the membrane? You cannot go across a membrane if you are an ion unless you have a channel that is open in the membrane specifically for that ion. Okay, so if you just had a plasma membrane with nothing in it, you could have 1,000-to-1 ratio of sodium on the inside to the outside, and the membrane potential would still be 0. Okay, because no ions would be able to flow across it. Okay. If we only had, and so now in the case of the membrane that has only potassium channels in it, okay? If you only have potassium channels in it, we just calculated what the equilibrium potential for potassium is, right? It's down here. Oops. Maybe I'll undo that. Well, okay. It's negative 90 millivolts from our previous thing. So if we only had potassium channels open, our membrane potential for the cell would be right here. It'd be down here at negative 90 millivolts. If we only had sodium channels open, okay, we had no potassium channels in it, okay, then our membrane potential would be here, plus 62 millivolts, because it's only permeable to sodium. What would happen if we only had chloride channels open? Well, we just calculated the chloride membrane potential, right? That was like negative 85. So it would sit down here. If we only had chloride open, it'd be hang out here around negative 85. Okay. Now, in a normal cell, okay, at rest, there's not only one set of ion channels that are open. Okay. What we're going to have to look at is basically the weighted average, okay, of each one of these equilibrium potentials. That's weighted on the proportion of the channels that are open on the membrane. How much of them are sodium channels? How many of them are potassium channels? How easy is it for sodium to pass through the membrane versus potassium to pass through the membrane versus chloride to pass through the membrane versus any other ionic species? Okay. At rest, most of the channels that are open in a membrane are potassium channels. Not all of them, most of them, maybe like 90%, 80% of them are potassium channels. And the rest, maybe there's a little bit of chloride channels, maybe there's some sodium channels that are open, okay? So we're gonna have the actual membrane potential of a neuron is gonna be a blend, a weighted average of the permeability, basically of each one of these equilibrium potentials multiplied by or weighted by the relative permeability of that. So if we're really permeable, so right now we have at rest, we've got a lot of potassium channels open. We have a few sodium channels open. Where might our membrane potential be? It's not going to be out here because it can't go out there because you can't go past this equilibrium potential, right? There's nothing that would draw it that way. Okay, the membrane potential is always going to move to some sort of blend between EK and ENA. So if we have mostly potassium channels open, it's going to be somewhere around here. Okay. If we were to close those potassium channels, okay, and just have more sodium channels open, what would happen to the membrane potential? It would go this direction, right? Because we'd start moving as we get more and more relative permeability of the membrane to sodium ions relative to potassium ions. We're going to tend to depolarize the membrane, move it towards, right now it's very polarized, it's very negative over here. We're going to move it that way towards the equilibrium potential for sodium. Okay. In fact, if we closed all the potassium channels and only had the sodium channels open, we'd make it all the way up here to plus 62. And if we open the potassium channels up again, close some sodium channels, we'd start moving back down. Back towards negative 90. Okay. And so at rest, at a membrane potential at rest, what we call the resting membrane potential, we're usually around negative 7 because most of the channels that are open are potassium channels. There's some sodium channels open. But in a neuron, unlike many other cells, In a neuron, in cardiac cells, there are ion channels that are going to dynamically open and close, that are going to push this membrane potential back and forth. Less negative, more negative over time. Yeah. And that's going to be the basis of the action potential. Now, one thing to note, the equilibrium potential for each ion never changes, okay? Because it only cares about the concentration difference between the inside and the outside of the cell, right? And the charge of that ion. Does the concentration change between the inside and the outside of the cell? You might think it does, right? Like if I look at this like little graph and I have 150 millimolar dissolved here, and I have 15 millimolar of sodium chloride dissolved here, and these sodium channels are open. The sodium ions are going that way, right? Isn't that going to change the ionic concentration? Yeah, a little bit, but like less than 0.01%. It doesn't take many ions to move across this membrane to actually create that membrane potential difference, to change the membrane potential. So for all intents and purposes, for this course, okay, and basically in life, okay, the sodium, the potassium, the chloride concentrations between the inside and the outside of the cell are always going to stay stable. It doesn't matter what's happening during an action potential, what ion channels are open or closed, because just there's so much sodium on the outside, and there's still a lot of sodium on the inside. 15 millimolar is still quite a bit of sodium, okay? So the few number of ions that have to flow across the membrane don't make any appreciable difference to the actual concentration ratios. So this does not change. Okay. Equilibrium potential does not change. What can change, though, is the membrane permeability to every ion. Okay. And that's what's going to bring us to the action potential. So this is a recording of a neuron, okay, of the membrane potential of a neuron. And this is intracellular recording, and we can look at a few things here. So first, this is the time scale, 1 second, is that bar there. This is millivolts, okay, this little scale bar there. So this neuron right here at this time point is at -63 millivolts, and you can see it fluctuates up and down, sort of slowly like this. And then every so often, there's this sharp spike that goes up way up to here. Okay, pretty high. We don't know exactly what that is. Maybe it's plus 30 millivolts, maybe plus 40 millivolts. And these fluctuations at the bottom here, these are called graded potentials. So there's sort of changes that go up and down in a narrow range. Okay. And they can fluctuate, whereas these spikes upwards tend to get to exactly the same level. Okay. And those spikes can happen at different rates. Sometimes you go a few seconds without having an action potential or a spike. Sometimes they come in a big burst, 10 in a row, really quick. Okay. And if we look carefully at this plot, what do we see? We see that whenever the membrane potential here is really low, okay, below -63 millivolts, it looks like we don't fire any spikes. And when it gets high, then we start seeing spikes. The higher it gets, the faster the spikes go. And so we need to understand, how are we going to get these variations? How do we get these small variations, these graded potential changes? And how do we get these spikes, these action potentials? What triggers those action potentials? Okay. Ultimately, how do these get sent down an axon? So the only thing that can change the membrane potential is what? Permeability. So we have to be changing permeability, right? We're not changing the ion concentration. So both this graded potential change and the action potentials are driven by changes in membrane permeability. Okay. Short-term, quick changes in membrane permeability. How can we change the membrane permeability? We've got to look at what different classes of ion channels exist in a membrane. Okay. We've talked about these potassium and sodium channels, okay, that are always open. We call these leak channels. They're leaky. Okay, they don't have any gates on them. They don't have a door to open or shut. They're just always there. If you have them expressed in the membrane, they're going to start, leaking stuff out. The more you have expressed in the membrane, the more leaky that membrane is, the more permeability to that specific ion you have. Okay, so most of the leaky channels are going to be potassium channels. Some will be sodium channels and some will be chloride channels. Okay, but since we're sitting near, since we're down at negative 70 millivolts, we know that most of the conductance, most of the permeability is potassium at rest. The resting membrane potential is controlled by these leaky channels. Okay, but not all channels just have a core and nothing else. Many channels, I'd say most channels, actually have gates. They have doors that can open or close, and how they open or close, how that opening and closing is triggered depends on the type of channel. So what's controlling the graded potentials that we saw, those fluctuations that are very low, okay, at these quite polarized potentials, those are generally caused by changes in ligand-gated channels, opening or closing. What's a ligand? It's just a chemical that can bind to a receptor or bind to another molecule and change the conformation of that molecule. Okay, so in the case of a ligand-gated channel, the channel is normally shut like this. Okay, here's a sodium channel, ligand-gated sodium channel. Okay, we have a ligand here. Oh, here it comes in. It's going to bind onto this binding site here, and the binding event causes a conformational change that opens a pore in the channel. That is going to now increase the conductance or increase the permeability, the ability for sodium ions, in this particular example, to pass through into the cell. If we open a sodium channel, do we expect the membrane potential to go down to more negative potentials or to go up to higher potentials? Well, diffusion is going to drive the ion across, but what will we expect the membrane potential to do? Go up. Why? Because there's more sodium moving into the cell, right? That's a positive ion moving into the cell, so it's going to tend to move it higher. How high do you think it could possibly get if we opened up only sodium? If we opened up a ton of sodium channels, what's the limit that we could go to? Plus 62, right? You're not going to go past that because it's acting like a magnet, and you get more. You're adding more magnets. You're pulling the membrane potential up towards 62 when you're opening up more sodium channel. What would happen if we had a ligand-gated potassium channel, though? If those opened instead, okay, then it would actually tend to pull us down towards negative 90 millivolts. Okay, and here's an example. You can call this, they call it signal gated here. There's a lot of potassium channels that can be activated by molecules inside the cell. Maybe a second messenger, for example, maybe they get phosphorylated or something. And those are also going to contribute to graded potentials. If you open up a potassium channel, you're going to tend to pull the membrane towards negative 90 millivolts, hyperpolarizing it. Yes?
So are the ligands like neurotransmitters?
Absolutely. Ligands are neurotransmitters. So the major ligands we'll be talking about in this course are glutamate. Okay, that is like the primary excitatory neurotransmitters are going to be glutamate and acetylcholine. Glutamate is really the dominant one in the central nervous system. Acetylcholine is the dominant one in the peripheral nervous system. The primary inhibitor, and those will tend to excite the cell because they're going to cause the membrane potential to go up. And then we have another neurotransmitter, GABA, which is an inhibitory neurotransmitter that is going to act on chloride channels. You can imagine if you open up a chloride channel, that's going to keep the membrane potential pretty hyperpolarized, pretty negative. Or, if the equilibrium potential is negative 85, it's going to try to hold it down there, right? Okay. So those are ligand-gated channels. We'll talk about them maybe at the end of this lecture, maybe in the next lecture in a little bit more detail about how that ligand binding works. But I want to get to the active potential. And this is where the voltage-gated channels come in. And this is where there's an example here of positive feedback. Okay. So a voltage-gated channel has got a gate or sometimes two gates, okay, that are sensitive not to something binding onto it, but to the actual membrane potential itself. Okay. So how much charge how much positive charge difference, or how much charge separation is there? How strong is the difference between the inside and the outside of this cell? Okay. And there's going to be electrically charged amino acids that have little sort of positive ions here that are in the pore of this, and they get pulled towards in one direction, towards the negative charges here, okay, and basically plug the hole, okay? But if the cell depolarizes, if the resting membrane potential goes up enough, okay, that can release some of that force that's pulling those charges in the pore, and it can allow the channel to open up, okay? Now you can imagine if this is a sodium channel that opens up, you might get more depolarization. You could have a positive feedback loop. This opens up, then the membrane potential goes up more. You're going to release more. You're going to release the sort of the voltage gate on all these other voltage gated channels. They're going to open up, and you're going to get suddenly shoot really fast up, right towards plus 62 millivolts. Okay, which is pretty close, right, to the peak here. That's pretty close to plus 62. Okay. Doesn't usually get all the way to plus 62 though, because there's more than one kind of voltage gated channel. The sodium channels are going to be the first ones that open up. They're the most sensitive, they're the fastest acting, but there's also voltage gated potassium channels. When those start opening up, guess what happens? The voltage is going to come back down, it's going to come more negative again, because now you're increasing the conductance of the membrane to potassium. You're going to pull the membrane potential back down towards negative 90. So the interplay between the opening and closing of the voltage-gated sodium channels and the potassium channels, the voltage-gated potassium channels, is what's going to drive these very fast spikes. Okay. Now, what's going to initiate those spikes, though, is going to be smaller depolarization, smaller increases in membrane potential from ligand-gated channels or these signal-gated channels. Okay, so let's take a little bit closer look at the structure of voltage-gated channels to see how this actually works. Okay, so here is a structure of a voltage-gated potassium channel. The structure was solved, like the actual crystal structure was solved by Rod McKinnon, maybe I remember like 20 years ago. He got the Nobel Prize for it. Very hard to crystallize proteins that are in a membrane because they have they're not soluble in normal solutions. So it's pretty tricky. And this channel has got these transmembrane domains that go backwards and forwards that cross the membrane a few times. Okay, and then right here, there's a paddle. There's a transmembrane domain that goes in and dips back out of the plasma membrane. And that is where the charged amino acids are. And that's the sensor for the membrane potential, because it needs to be in the membrane. It has to sense the difference between the outside and the inside leaflet of the plasma membrane. So it embeds itself in there, in the protein. And that can flip open or close like a little paddle in pinball or something, okay? Now, these voltage-gated potassium channels are actually a tetramer. Okay, so they have 4 of these sort of pieces coming together. So they have 4 of these little paddles sticking in there. And together, they're going to make the pore, the voltage-sensitive element of the pore. Okay. So remember, at rest, we've got our leaky channels are going to be potassium channels, some sodium channels. Okay, the leaky channels don't have this gate. Okay, they're just boring leaky channels. Okay, and the action potential is going to depend on how voltage-gated potassium channels and sodium channels open up. So let's look a little bit more closely at the voltage-gated channel. What does it actually look like, the shape? Once we put these sort of 4 pieces together, these 4 protein components come together, this is what it looks like. You have sort of this barrel that penetrates the membrane, okay? And then you have a passageway or a pore that's going to allow charged ions to flow across. Now, it's actually pretty hard to get charged ions to flow across a membrane because in order to do so, you have to rip off the water molecules that are stuck to them, right? Water is a polar molecule, and ion, it has a sort of a dipole that has a positive side and a negative side, right? And so any charged ionic species in water is going to be hydrated. There's going to be a shell of water molecules around it, stuck to it. Okay. And the design of any of these ion channels is such that it has just the perfect shape and the perfect sort of organization of electron cloud along the inside of this pore that will allow the water molecules to fall off of this ion and coordinate with the pore itself in a very low energy way. Okay. And so the exact shape of this pore is going to determine the selectivity of this ion channel to what ion it will allow it to pass. So the potassium channels are going to have a little bit different shape here on the inside of the pore than sodium channels or chloride channels. And in fact, but there's also going to be channels where they'll pass both potassium and sodium, either one. Okay, they can go in either direction. Okay, so this is basically just sort of lowering the transition energy that is required to pull these shells of water off of the ion and allow them to flow past down their concentration or down their electrochemical gradient, I should, concentration and electrical gradient. Yes.
Claiming the channel is random icon block,
How do they maintain the channel if random what blocks it?
like a random icon have a bigger size.
What's a chiton? Oh, cation?
Yeah, cation.
Oh, well, I mean, the cation is the potassium here. Okay, are we talking about these here?
No, like the red one.
Okay.
With a bigger size cation.
Oh, okay, right. So these cations, right? So different ions have got different sort of sizes of their electron cloud and different densities to how far those attach, right? It's really just a matter of, I mean, it's probably some complicated calculation that it's not just like the size of the ion species, it's also how many like water molecules can fit around it and what the shape of that shell looks like, right? And I think it's probably, I don't even know if it's fully understood, right? Because you'd have to do some sort of quantum calculation to know exactly how those things are going to interact with each other, okay? And oftentimes, and sometimes when you like get a crystal structure of these things, you'll see a few water molecules that are stuck in place that are always in the same spot, and then a bunch that are disordered and they won't show up in the crystal. Okay, so depending on your charge, okay, and the overall size of that ionic species here, you're going to have a little bit different shape and pattern of charges along the pore to allow the ion to pass. That's how we're going to get the selectivity of this. Okay, but in a voltage, and that's true for all ion channels. Okay, now we have to have a voltage gate though in the voltage gated channels, and we have one or sometimes two voltage gates. Okay, the first gate, which all these voltage gated channels has, is the paddle. Okay, that's inside the pore. Okay, when there's a depolarization, the paddle flips up because it's not being pulled into the inside of the cell as much, and that is going to then allow ions to flow through. Now there's a second gate sometimes that's present on a lot of voltage gated sodium channels, on some voltage gated potassium channels, and this is called the inactivation gate. You ever played with like one of these, like try to catch a ball on a string in a cup? It's exactly this sort of situation here, except we're upside down and the ball wants to go in. So this ball basically floats, or this is the inactivation gate, and it can clog the pore here. But it'll only clog the pore at particular membrane voltages and at particular times, and it happens at a different pace that the activation gate will open or close at. Okay, so in order to have ions flowing, we have to have both this activation gate open, okay, so the ions can flow here, and we have to have this ball and chain unplugged from this sort of drain here, okay? So in this case, we cannot get any ions to pass through. In this case, we also can't get any ions to pass through, but it's two different gates that are causing the blockage. So let's look and see how those gates open and close at different membrane potentials and at different speeds. So here's a little sort of sketch of a voltage gated sodium channel. Okay. At rest, okay, if we're at a for a normal, if we're at rest, the resting membrane potential, we're down at, say, negative 70 millivolts down here. Okay, negative 70. The normal state of a voltage gated sodium channel at rest is that it is closed. Okay, it's deactivated. Okay, because this activation gate is closed. Nothing can pass through here, right? If the membrane potential depolarizes, goes more positive to a particular, past a little threshold. Okay, it depends on exactly what the threshold sort of depends from ion channel to ion channel. Okay, maybe we're up at negative 50 millivolts or so. Okay, then our activation gate opens right here, and ions can flow through. Sodium ions can get into the cell, right? Okay, that is going to cause more depolarization of the cell, increase in membrane voltage. Okay, and that will continue to allow sodium ions to pass through until this inactivation gate plugs the hole. So the inactivation gate likes to plug the hole when the membrane potential is high, whereas the activation gate will plug the pore when membrane potential is low. Okay. So in order to get the membrane potential high, we have to get a small depolarization that then triggers this positive response. Now this voltage gated channel opens up, ions flow, they flow for about a millisecond or so, and then the inactivation gate plugs the hole. Okay, that's going to stop the sodium ions from flowing, and then the cell will tend to repolarize, decreasing the membrane potential because we are now reducing the permeability of the membrane to sodium. Okay, and that's going to then close this activation gate. Okay, so now it's blocked in two different ways. And then it's going to take a few milliseconds of sitting around here at these more negative potentials for the inactivation gate to fall off. The inactivation gate's a little bit stickier than this activation gate, so to speak. Yeah.
Different activation voltage.
Right. They have different activation voltage, and they have different kinetics of activation. So the activation gate, okay, opens and closes much faster. The inactivation gate is a little bit slower. The activation gate opens up at high membrane voltages, closes at low membrane voltages. The inactivation gate closes at high membrane voltages and releases at low membrane voltages. So this interplay between the timing of this is what allows the voltage gated sodium channels to open up briefly, but not hang out open all the time. If we didn't have this inactivation gate, what would happen? We get a depolarization, our channels would open up, we get our depolarization, and then we just stay really high because the ions just keep flowing in. Okay, we've got no reason to close. Okay, we have to have a second gate that closes when we're high. Okay. Does that make sense? Any questions about this? Okay, so how do we measure an action potential? What are we actually looking at? Okay, we have to measure the inside and the outside of the cell. Okay, so measuring the outside of the cell is really easy. Okay, you can just put a little piece of wire in like a fluid that surrounds a salty fluid that surrounds the cell. Okay, and that's where we're going to measure our reference. That's the outside. Getting a wire into the cell is pretty tricky, as you might imagine. It's got to be a really thin wire. Well, actually, no, you can't make wires that thin. They're not stiff enough to actually poke into a cell. So what you end up doing is slipping a wire into a little piece of tube of glass that's been pulled so that the tip of it is really, 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 really tiny, like a micron across, like 1/100th of the width of a human hair. And you fill that, what we call a micropipette or microelectrode, with salt water. Okay, and now if you poke it into the cell, you can now measure the inside of the cell, what the electrical level is on the inside of the cell relative to the outside of the cell. Okay, and that's what will allow us to view the fluctuating membrane voltages. So let's take a look and see, what do those membrane voltages look like? Okay, let's assume there's a stimulus here. Okay. And here's a plot of our membrane potential. So membrane potential is always measured by what is the difference between the inside of the cell and the outside of the cell. So if it's negative, that means the inside is more negative than the outside. That's the way it normally is, right? All your polarized cells in your body are usually negative. Okay. So we're sitting here at a negative membrane potential, about negative 70 millivolts, pretty typical, okay? And then something is going to happen right here at time equals 0, okay? And what happens is that there is some hyperpolarization that occurs here. The membrane potential goes down. What could cause that? Any ideas? Is that a voltage gated channel opening up?
Maybe the delay of voltage.
Nope. Nope. What could cause a hyperpolarization? You're just sitting here at negative 70 millivolts. What change in permeability would there have to be?
Ligand, like, or let's.
Yeah, it could be a ligand letting chlorine in or a potassium channel opening up. Something that's pulling the membrane potential towards the equilibrium potential for chloride or potassium. Remember, EK is down here. ECl is like here. Equilibrium potential for sodium is like up here. Okay, so if we're going to hyperpolarizing, we know that some channel had to open up. Okay, since there is no change in membrane voltage right here, it's unlikely that that channel is a voltage gated channel, right? Because the voltage change is what causes a voltage gated channel to open. It has to be something else. So it could be a ligand binding onto it. Maybe it's GABA binding onto a chloride receptor or GABA receptor chloride channel. Maybe it is one of these intracellular signaling molecules opening up a potassium channel. We don't know. We just know that there's a hyperpolarization. So we know that there had to be an increase in the conductance to either potassium or chloride. Yes.
Oh, so is hyperpolarization like around the same potential every time?
There's two. Okay, well, what happens? So if we opened up a few channels, we get a small hyperpolarization. If you open up more channels, you get more hyperpolarization. If you opened up all the channels, okay, all of the potassium channels, we're going to go to here. But we're not going below there, right? Because we're not going to, whenever you open up the channel, you're moving to the equilibrium potential. You're not just because you open up a potassium channel doesn't mean you're going to go like always negative. If you started at like a negative 120 for whatever reason, and maybe you were somehow controlling the membrane voltage and you're negative 120 and you opened up a potassium channels, it would actually go up. It would actually depolarize towards negative 90 because you'd be increasing the conductance for that particular channel. That's not what normally would occur in the brain, but if it did, like that's what would happen. Yeah. I would say that in this case, it's not voltage gated because a voltage gate requires there to be probably, in order to trigger a change in it, there's probably going to be a change in voltage in order to make that thing open up, right? So we'll see a voltage gated, how change in voltage in a second can trigger the opening of voltage gated channel and the running away of this. So we're just assuming since there was no change in voltage right here, there'd be no reason for the state of a voltage gated channel to change. Does that make sense? Yeah. Yeah. Could a chloride channel and a potassium channel open at the same time? Yes. Absolutely.
Well, that'll lead to an even more negative.
Maybe it depends. Actually, so the chloride channels actually sometimes it really depends on the concentration of chloride. Sometimes the equilibrium potential for chloride is a little bit higher, like negative 70 millivolts. And that can just sort of pin the cell to negative 70 millivolts if you open it up, right? So you might not go even you're going to always be moving towards whatever the equilibrium potential is for the channel that's opening up. Okay, you're going to tend to move in that direction. So if you're starting up here, absolutely, chloride or potassium is always going to be hyperpolarizing to you. But if you were starting like here, then opening up a chloride channel is not going to change the membrane potential at all. But it still might inhibit the cell from fluctuating because you have a greater conductance or a greater permeability for chloride. You'll tend to hold it at that equilibrium potential because it's always the membrane potential is always a weighted average of the different permeabilities times their equilibrium potentials. Okay, so that's hyperpolarizations. Okay, What about depolarizations? These graded changes, these small changes, these fluctuations are exactly what we were seeing. Okay, so well, I guess so these depolarizations, what could be happening here? More ligand-gated channels, right? Some other ligand-gated channels. And what do we think the conductance there might be? We must be increasing the permeability, the relative amount of sodium permeability in the membrane, because we're moving towards plus 62. So maybe a glutamate molecule came out and bound to some ligand-gated channel that binds glutamate. Okay, that opens up a channel and is allowing sodium in, and we get a depolarization. Okay, so these are the graded depolarizations that we see. So these ligand and signal-gated channels are what's causing these small fluctuations down here, right? This is basically just a whole bunch of ligand-gated channels opening and shutting, or those signal-gated channels opening and shutting, okay? You're just bouncing around here. But there is a level at which something dramatically different happens. Yeah.
So I know that a voltage gated channel is only gonna open, but when the ligand channels open, that is a change in voltage, just.
Mhm.
There's gonna be a delayed. opening.
Great question. So the ligand-gated channel is the change in voltage from the ligand-gated channel is going to be what triggers a voltage-gated channel to open up. Exactly right. Okay. So here we go. So we've got our small depolarizations. If these depolarizations are small, okay, below some nebulous threshold here, they are not going to be enough to open up the voltage-gated channels. But if they get over this threshold, maybe it's negative 55 millivolts or so. It really depends on the channel. What do we see? We see a sudden runaway depolarization. Okay. This is the action potential. This is the spike. When we get up to this threshold from enough ligand-gated channels opening up, all of a sudden our voltage-gated channels start opening up. That is going to cause further depolarization. That's going to cause further voltage-gated channels to open up, further sodium channels opening up, and boom, we're going to shoot up really close. We're going to be well on our way to plus 62 millivolts within 100, 200 microseconds. Super fast, okay? But we never quite make it there for two reasons. Reason number one, the sodium channels start to inactivate because they have that second gate. And reason number two is that there's not just voltage-gated sodium channels in the membrane. We also have voltage-gated potassium channels. They're a little bit slower than the sodium channels, though. So let's take a look at this. Let's look at these sort of steps here in this process. So we've got our extracellular fluid here, we've got our inactivation loop, and we're going to sort of display here the voltage-gated sodium and potassium channels that are in the membrane, okay? At negative 70 millivolts, our resting membrane potential, what do we have here? We have our sodium channels, potassium channels. They're not inactivated here. The inactivation loop is flopping around. It's not plugging anything up because we're at a very negative potential, okay? Okay, sodium ions can't get in, potassium ions can't get out. Nothing's really happening. Now, then that's this state here. This is step one, phase one. We're at rest, steady state. Okay, if we get some sort of depolarization that takes place by some ligand-gated channel that's not illustrated here, our voltage, is this a ligand-gated channel? Well, whatever. If we get some sort of depolarization, now some of these voltage-gated channels start to open up. Sodium ions are going to pass in, okay, which is going to cause a further depolarization, making the inside more positive than it was before, which is going to cause more voltage-gated channels opening up, okay, which will cause more depolarization, and that is going to cause this shoot upwards from all of this rising phase of the action potential, very fast, 100 microseconds. Okay. Now, after that is occurring, okay, we have this falling phase of the action potential, which is driven both by an activation of sodium channels, closing up, and the opening of these voltage-gated potassium channels that allow positive potassium ions to flow out. If positive ions are going out, then the membrane potential is going to become more negative again. Okay. And then actually, usually the action potential goes even more negative than the resting membrane potential. Okay, and why might that be? It's because we have the normal channels that are open at rest are those the leaky channels. There's a lot of sodium, a lot of potassium channels open, a few sodium channels open that they're leaky. They don't have any gates. Those don't change during this process. Now all of our sodium channels are inactivated, they're closed, but we still have a few potassium, voltage-gated potassium channels open. Okay, so that tends to bring that membrane permeability for potassium higher than it normally is. And that brings the membrane potential down closer to negative 90 millivolts than it usually is. And that'll last for a few milliseconds until these voltage-gated potassium channels close up. Okay. So this is sort of a written sort of sequence of events that I just stated. And an important concept here, though, that we haven't talked about yet is the refractory period. So this is a period in which after you fire one action potential, it's hard to fire a second action potential. Now, why might that be? That is going to be because during the first few milliseconds after an action potential, most of our voltage-gated sodium channels are plugged and their inactivation gate is plugged. And it's going to take a few milliseconds for this to unplug itself here so that if you get a depolarization again, you'll be able to open up this gate and allow ions to flow. If this gate is open and this plug is closed, like there's not going to be any current, not going to be any ions flowing. So that refractory period is dependent on how quickly a sodium channel is going to de-inactivate for the inactivation gate to the plug to fall out. So all of this can be explained in this one slide. If you can fully understand just the slide, you're in great shape. You know, you're going to be on the level of, you know, an incoming graduate student probably in neuroscience. So, but this is a complicated slide. So I'm going to walk through each step, and this is the sort of the grand summary of action potential. So what do we have here? We up here, okay, this is the state of the channels, okay, of voltage-gated sodium and potassium channels, okay? And, you know, voltage-gated sodium and potassium channels, they can either be open, they can be closed. They're never halfway, okay? The gates either open or closed, right? They change in microseconds, okay? But there's lots of them, right? So like different ones will be opening and closing at the same time. Here is the membrane potential in red, okay? And in gold and in purple here, this is the Lakers colors, okay? We have the changes in ion permeability, okay? Specific to potassium and to sodium. And then down here, we have how excitable is the neuron? How easy is it for it to fire an action potential? Okay, so before an action potential takes place, okay, all of our voltage-gated channels are closed and our sodium channels are de-inactivated. They're not inactivated, okay? So they're available to open up if we got a depolarization. Where they're available to pass current, we only have one gate blocking it, okay? So when we get some sort of depolarization and we cross this threshold here, our sodium, voltage-gated sodium channels are going to open up and we're going to start sending our membrane potential here in red much higher. Now, why is it going up? It's because the sodium permeability is going up, right? The membrane potential at any given time is always going to depend on how permeable your membrane is to sodium and potassium and chloride. Right? So if your membrane permeability for sodium is going up and your membrane permeability for potassium staying the same because the channels aren't open yet, that means we're going to tend to move towards the equilibrium potential for sodium, right? We're shifting the balance of permeability towards sodium because this ratio here of sodium to potassium is really going up very quickly, okay? When we hit the peak of the action potential, that is the point where you're at the highest sort of, the sodium permeability is the very highest compared to the permeability for potassium. Does that make sense? Okay. So we can see here, this sort of permeability is sort of a measurement of how many sodium channels are open in the membrane at a given time. And the potassium permeability is how many potassium channels are open in the membrane at a given time. Okay, so our sodium permeability shoots way up, our action potential shoots up high, 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 high. It gets to right about here. And two things are happening at the same time. One is that our sodium channels are inactivating, they're starting to get clogged. Okay, so our sodium permeability starts falling, and our lazy potassium, voltage-gated potassium channels are finally getting around to opening up. Okay, so they start opening up. Okay, they open up at high membrane potentials. It just takes them longer to get going. Okay, so we've depolarized now. Okay, our voltage-gated potassium channels are opening up. Our permeability for potassium is going up, while our sodium permeability is going down. And boom, okay, at some point here, the sodium permeability goes back down to basically baseline, okay? But our potassium permeability is still high because our voltage-gated potassium channels are still open, okay? That's why we're gonna get this undershoot here, where we go below our normal level of voltage, okay? Here in red. And then after a few milliseconds, the voltage-gated potassium channels will close down, and our membrane potential will go back to baseline, where at baseline, the only channels that are open are those leaky channels. So that's most of what this plot is. You have a question?
What is the difference between the top of the sodium line and then the action? The action potential is a little higher.
So these are two different axes that are overlaid on top of one another. So the action potential is going to be the membrane and potential, and then this this potassium. So why is there an offset between this peak and this? Is there there is maybe a little bit of an offset there between there and there. It's about the same. I don't know. Okay, I think there's maybe a tiny little offset here by like 100 milliseconds, or 100 microseconds, where the sodium. I don't know. I'm not sure if that's meaningful or not. Okay, good question, but basically the sodium, maybe there's some delay in how quickly the sodium gets in and changes the membrane potential on the order of microseconds. Okay. Okay, so this plot is our membrane potential conductances, and now the last part here is the excitability. Okay, this excitability is dependent on how available are the sodium channels for opening up. Okay, so when the sodium channels inactivate, okay, if all the sodium channels get inactivated, okay, plugged, then you're not going to be able to fire an action potential. Okay, because even if you had a depolarization, the sodium channels, the voltage-gated sodium channels are not available to pass ions. Okay. Now, as the sodium channels deactivate, this thing always does. As the sodium channels deactivate, okay, so they become more and more available over the next few milliseconds. So in this sort of window of time, the excitability of the cell starts going up until all of our sodium channels are deactivated. They're all available again, okay? And that is when you're going to be the most sensitive, okay? So when you're here, okay, at this sort of stage, you're in high level of sensitivity. All your voltage-gated sodium channels are available if there was a depolarization. Then it's easy to fire an action potential. The threshold of depolarization that you need to get this runaway excitation is pretty low, negative 55 millivolts. Shortly after an action potential, okay, maybe only half, like right here, only half of your voltage-gated sodium channels are deactivated. They're ready to go. So you would have to have more of a depolarization, a stronger amount of ligand-gated action to drive an action potential again. Okay. So that makes it harder to fire action potentials at very high rates of speed. You have to have a much bigger depolarization than to fire at lower sort of rates. Okay. So this is called the absolute refractory period, where you cannot initiate another action potential. And this is the relative refractory period, where it's difficult but not impossible. And it gets easier and easier until it's the easiest back when all of our sodium channels are deactivated. Question? No, most cells in the body cannot generate action potentials. The cells that can are cardiac myocytes and the Purkinje, those Purkinje fibers, the electrical fibers that go into the cardiac myocytes, the neurons, and oh God, what were the other one? Cardiac myocytes, neurons, and muscles. Okay, those are the primary tissues. Maybe there's a few more that could have some sort of dynamic changes from voltage-gated channels, but those are the key players. Okay, most cells are just going to sit around at the resting membrane potential. Okay, any other questions about this slide? This is a complicated slide. Those are all the concepts that you need to know, though, about membrane potential, action potentials, all in one place. Okay, so an action potential is pretty cool. Okay, you've got this dynamic fluctuating change, and that's great, but it doesn't send a message anywhere. In order to actually send electrical messages, we've got to put those spikes and send them down a wire. Okay. We want to send these spikes down a wire. This is a digital signal, these pulses. It's got to go down a wire. How are we going to get down the wire? This is the concept of conduction along an axon. Okay, so let's imagine what happens. So before we were just looking at one single little piece of a membrane. Okay, but an axon is not one little piece of membrane. It's a long tube of membrane. Okay, and along that membrane we have voltage-gated sodium and potassium channels all along that length. Okay. Now, if we start an action potential here, okay, we get some sort of depolarization. Where does that depolarization come from? All of those ligand-gated channels, most of the ligand-gated channels are sitting here on the dendrites. They're sitting there waiting for chemical neurotransmitters to land on them, cause some hyperpolarization or depolarization. If you've got enough depolarization, it all adds up and causes a depolarization here, and that's going to cause the action potential to get launched. And that action potential is then going to travel in a wave down the axon. Why does it travel in a wave down the axon? Because if we start an action potential here, okay, what will happen? We're going to have sodium ions flow into the membrane. It's going to depolarize this patch of membrane. And those sodium ions are going to try to leak out of the membrane eventually. Okay, they're going to spread sideways, laterally, okay, down the membrane. That will tend to depolarize the neighboring patch of membrane and trigger voltage-gated channels there to start opening up. So we have the sodium comes in first, okay, it spreads out, you get a depolarization here, it spreads out a bit, the neighboring patch of membrane then starts to depolarize, that causes voltage-gated channels to open up there, that causes this to depolarize, okay? And meanwhile, back here, so this is like at, 0 milliseconds in, now let's say this is like 1 millisecond in. Okay, now we've got all these potassium ions coming out. This is repolarizing here. It's getting more negative again. This is depolarizing. Okay, and then this causes a depolarization of its neighbors, the sodium ions coming in. That triggers the voltage-gated sodium channels here to open up, which causes this patch of membrane to go off. Now, why doesn't it keep going? Why doesn't it go backwards? Okay, well, that's because the sodium channels back here are inactivated, right? They after they open up, right? They get inactivated for a few milliseconds. So you can't go backwards because those sodium channels are inactivated. So you have this wave of voltage-gated sodium channels opening up, followed tightly behind by a wave of voltage-gated potassium channels opening up and the voltage-gated sodium channels inactivating. So the action potentials are always going to move away from the site of action potential initiation. When they get to the end here of the axon, they don't bounce back because there's these inactivated sodium channels. So normally in all of those interneurons that we've been talking about, the action potential is initiated here at the axon hillock. Okay, so we've got these incoming depolarizations from our ligand-gated channels, chemicals landing on the cell that makes it to the axon hillock. The axon hillock is the most sensitive part. It has the most voltage-gated sodium channels. So the threshold for initiating the action potential is the lowest there. It's the easiest to cause it to fire. That's why it starts there. And then zoom, they zip down this way. Okay. But I have a question for you. Thought experiment. Thought experiment. What would happen if for whatever reason we got some depolarization here on the tips without an action potential generated here? Would we be able to generate an action potential in the tips? We got a strong depolarization. If there are voltage gated sodium channels and they're not inactivated, yes, you can cause an action potential there. Okay. So if we somehow cause the depolarization on the tips here, okay, we could actually generate an action potential that would zip backwards, go back this way, because this area would not be inactivated, right? What's up?
What if there are like two potentials happening at this side?
Great question. What would happen if two action potentials happen at the same time? What would start here? One starts here. Are they going to pass by each other? Are they going to bounce off each other? Are they going to annihilate each other? And what do we think? Who thinks they're going to go past each other? Raise your hand. Who thinks they would? Okay. Do you think they're going to go past each other?
No, I think it depends on the current or like the. Like how high the voltage is.
Okay, so there's one theory is, okay, it will depend on which one's stronger, which is a stronger action potential, which one goes up higher. Guess what? All action potentials are the same. Look, they all go to the same spot. They're all equal in power. Okay, every action potential, because it's part of the intrinsic sort of nature of the sets of voltage gated channels. Okay, they're all going up to the same level. Okay, the only thing that changes in the action potential is how many you're firing per second. Okay, so you've got this wave of depolarization going this way and a wave of inactivation following it. And we've got a wave coming from the other direction of depolarization and inactivation following it. When they run into each other, they're just going to stop because they can't pass each other because they're each direction is running into an area of inactivated sodium channels. In fact, that is a technique that you can use in neuroscience if you're recording from one area far away and recording an area over here to try to prove that those two areas are connected, because you can cancel out the propagation of an action potential by triggering an action potential in the receiving zone. And I should also say, okay, so what slide is this, 53? I should also say that that remember when we looked at the morphology of these neurons, okay? These central nervous system neurons, this is how it usually works. But the sensory neurons actually work by triggering action potential sort of out in the tips, right? So if we look at the morphology of these sensory neurons, they've got receptors, mechanoreceptors or olfactory or ligand-gated receptors out here at the tip of I mean, it's called a dendrite, but it's basically, the dendrite's what's taking information in. But in a sensory neuron, the action potential is not initiated right here. It's initiated out at the sort of periphery, and that will then cause a propagation of the action potential this direction all the way past the cell body to these synaptic endings. So sensory neurons are a specialized form of neuron that allows the initiation of action potentials in the periphery and the propagation of that down an axon. So they're weird. It's like they've got an axon going in two different directions. All right. So that's talking about the propagation of unidirectional propagation. Now, there are some specializations of axons that allow that propagation to take place very quickly in the peripheral nervous system and in some parts of the central nervous system. Why do we have these Schwann cells and oligodendrocytes, these glias that wrap, like wrapping our axon in saran wraps? So here's an axon here on the inside. So slice through the axon, okay? And then we've got all these little wrappers around it. That is insulation. That is preventing any ions from leaking out of that membrane right there, okay? And So here's a Schwann cell wrapping around this, but it doesn't wrap the entire axon. Okay, it just wraps little sections of the axon, and then it leaves sections of the axon exposed. Those sections of the axons that are exposed are called the nodes of Ranvier. Okay, and this is sort of an electron micrograph of that. These are our nodes, and what's going to happen is the cell is going to concentrate its voltage-gated ion channels, sodium channels and potassium channels at these nodes, okay? And leave them out of the membrane in this part. Okay, we don't need them there. It's wrapped up. No, it's all sort of sealed up. It can't talk to the extracellular space, so it cannot have a wave of electrical. It can't pass any ions there. So these sort of gaps here are perfectly spaced so that when sodium ions come into the cell here, they travel laterally. They can't travel, there's diffusion, right? There's also sort of the difference that the electrical signal of those ions has a particular characteristic length, okay, that it can go. It can't go like a millimeter. It can go, I don't know, 20 microns or so, okay? It can easily sort of travel there. So it sort of creates an electrical current that falls off with distance, but it's just enough so that it can trigger the voltage-gated channels in that next node to open up. So the ions don't have to flow all the way down to there. They can, the electrical current that comes into here produces an electric field that triggers the opening of the ion channels in that next node. Okay, and that makes it much faster. This is called a process called saltatory conduction. It's basically like a chain of firecrackers that are going off in a wave. Okay, where one pops the next one and pops the next one to go off. And so that causes a much faster propagation of the wave than you would see if they were not myelinated. So we see myelination anywhere an axon has to go very long distances, you're going to see myelination on it because it has to go much faster. To coordinate your body, if you had unmyelinated axons, it would take a second for the information to get from your brain to your feet. That's not fast enough. Okay, maybe I think you can move about 1 meter per second. An unmyelinated axon, maybe about 10 or 20 meters per second in a myelinated axon. So way faster. So even though it takes up space to wrap around these axons, it is improving the conduction speed, and that's why we have it. Yeah. Now, what happens if that wrapper starts to degrade? Okay. This is the basis of multiple sclerosis. Okay, so if your myelin sheaths start degrading, that is going to slow down the conduction velocity of these axons. Okay, and that is then going to lead to an incoordination and inability to control your muscles in a coordinated way. Can eventually lead to, buildup of fluid in the lungs, difficulty walking, difficulty breathing, and so on. Okay. Now, let's see. I'm tempted. Is there any questions about this part? Okay, I'm going to then, I'm going to do it. Let's do it. Let's go to the next lecture. Okay. It's all part of the same lecture pretty much. Okay. And I want to just get started a little bit on this next one. Which is really, I should have just put it all in one thing. Okay. How do I zoom? Sure. Come back. Where's my zoom? I need to share my screen. Can't figure out how to, okay, there we go. Share desktop zoom. Okay. So let's take a look here. So how are we going to actually generate those action potentials, those ligand-gated channels? What were those ligands, right? Those ligands are coming, where do they come from? They're coming from synapses. They're coming from the connections between the axon to the dendrite. And what does a synapse look like? Here's our electron micrograph of a synapse. Okay, what do we have? We've got mitochondria right here, the powerhouse of the cell, right? Making ATP, releasing vesicles and packing vesicles full of neurotransmitters, very energetically painful. Okay, so all of these little vesicles here, there's a presynaptic terminal that is going to be releasing neurotransmitter into this synaptic cleft here, which will then cross it over very quickly in microseconds, and then open up ligand-gated channels here to cause depolarization of our postsynaptic dendrite. What does that vesicle look like? Each one of those balls looks like this. Okay, you've got a bunch of different proteins on it. You got this thing here. This is a transporter protein. This is what's going to, the engine that's going to pump this ball full of neurotransmitter, full of ligand. Okay, it's going to spend a lot of ATP doing that, and it's going to get the concentration of, say, glutamate or GABA inside here extremely high relative to the inside of the cell. So these vesicles are going to be stored at the ends of our axons, at these presynaptic terminals. And when that axon has an electrical wave that comes in here, what we will see is that calcium channels open up that are voltage gated. So we've talked about all these other voltage gated channels. Calcium channels can also be voltage gated. That will cause calcium influx to come in. The calcium will trigger the fusion of these vesicles to release ligand into the synaptic membrane, the synaptic cleft, open up ligand-gated channels, and then causing ions to flow. Yeah. And, you know, I'm going to stop. I'll stop there. We'll get into that this in greater detail. I know, you know, I should put it all on one slide, but it's good. Okay, next week we're going to talk about synaptic transmission and basically what the ligands do, how do they affect parts of the brain, and then the motor system, and then we'll be done. So we've got 2 quizzes left. One on Friday, don't forget. Okay, that'll be on these 2 topics, and then we'll have one next Friday. Thank you.
Channel 3.
Anti what?
Anti-porter?
An antiporter. Oh, I don't think that's an antiporter. That is a cation. So that is a